All right. I haven't got the book scanned to my liking, and I've been busy. I'm not making excuses, but I'm making excuses, all right? So just bear with me, all right? I got to keep reading this book. I'm not here to play around on a computer. I'm here to read a book, and I can procrastinate on even reading the book because I can always be like, oh, I haven't got time to get it out right. Well, that's bullshit. So, chapter 1, sound waves and vibration. If you need pictures, you should buy the book. This should be a no-brainer. But until then, 1, sound waves and vibration. We are constantly surrounded by sound. We even have a highly specialized opening in our heads for making sounds that may be meaningful to other people. We communicate through sound. In fact, it is our major means of communication. When we disturb the air in any way, we create sound. The slightest motion of our bodies disturbs the air around us, and we produce sound. When we raise our hand, we compress the air in its way, and that compressed air front will travel away from us at the speed of sound, which in air is about 740 miles per hour. When we make periodic movements with our hand, the sound becomes a note. By sound, we mean here any random acoustical disturbance that may be composed of many different frequencies. A note, on the other hand, is a sound of a single frequency. We call this kind of sound infrasound. That is, sound below our level of perception. However, when a fly or a mosquito beats its wings, it does it fast enough, and we are sure we sure can hear it. The rapid flapping of its wings produced evenly spaced compressions and rarefications of the air that become audible to us. In short, a fly or a mosquito is producing a sound or note. A little picture of a mosquito down there. Let us try to make sound in a less obvious way. We shall take a short piece of wire, connect both ends to a battery through a switch, figure 1, close the switch. We were told in school that 3 things happen. 1, that electrical current will run from one side of the battery to the other. 2, that a magnetic field perpendicular to that current will shoot out and expand all the way to infinity at the velocity of light, which is about 186,000 miles per second, and 3, that the wire will heat up slightly. They probably did not tell us 4, that when the wire heats up, it expands, and by so doing, it will clearly force the air out of its way and make a kind of sound. Or 5, that as the mass of the wire is accelerated in this way, it will produce gravitational waves. Since any time a mass is accelerated, it will broadcast gravitational waves, which will again expand to infinity at the velocity of light. Some will say that the gravitational waves will certainly be almost infinitesimally weak, but that does not worry us as long as they are there. So our action of closing the switch has been broadcast, theoretically at least, to the outer limits of the atmosphere around the Earth due to the movement of the air, and was broadcast all the way to the end of the universe by the expansion of the magnetic field around the wire and by the gravitational wave due to the wire's acceleration. The purpose of this example is to show how, in principle, even our smallest, most insignificant actions will be broadcast far and wide and thus influence something or someone, whether that something or someone is aware of it or not. We should look now at other effects of sound. If we stretch a string on a frame, figure 2a, then pluck the string in the middle of its length, we shall see the outline of the string in the extreme positions of its movement. It forms 2 symmetrical arcs as shown. If we pluck the string at the 1/4 mark of its length, we shall see a shape as in figure 2b. These are standing waves. We get such waves only when plucking the string at distances that will divide the string into integral numbers. In figure 2a, the frame length corresponds to half a wave, while in figure 2b, the frame accommodates a full wavelength. To B, the string has a point in the middle at which the string is at rest and 2 more points at which it is attached to the frame. What? Let's see. I hate restarting. In the middle at which the string... In figure 2b, the string has a point in the middle at which the string is at rest and 2 more points at which it is attached to the frame. Such points of rest are called nodes. All the other points of the string are vibrating up and down. When the nodes along the string appear stationary and fixed while the rest of the string is vibrating, we call such a behavior a standing wave. Suppose we now take a thin sheet of metal, figure 3, clamp it at one edge so that it stays in a horizontal position, spread some dry sand evenly over the sheet, then take a violin bow and draw it over one of the free edges of the sheet until it emits a note. Very soon we shall see that the sand grains are collecting on the sheet in a symmetrical pattern. As we apply the bow at different points along the edge of the metal, we shall get different and quite beautiful patterns on the sheet. The reason for this aggregation of sand grains is that we are setting up the so-called standing waves in the metal. These standing waves in the metal sheet are two-dimensional versions of the standing wave in the string. These standing waves have active areas that vibrate up and down and other areas or nodes that are quiescent. The sand grains will move away from the vibrating areas and accumulate in the quiescent areas. The sand grains like to be left in peace, and they will go to the quiet, low-energy places. This pattern in sand actually outlines for us the pattern of standing waves in the metal sheet. The standing waves automatically divide the length and width of the plate into the integral number of half-wave lengths, figure 4. It is only then that a standing wave can be sustained. This is so by definition. Standing waves cannot exist unless they divide their medium into an integral number of half-waves. A standing wave having a fractional wavelength cannot be sustained. We can also put it another way. The dimensions of the plate are the factors that govern what is the size or wavelength of the standing wave that can be sustained in the plate. When a structure is in resonance, which means that it vibrates at a frequency that is natural to it and is most easily sustained by it, it implies the presence of a standing wave. Let us see if we can visualize this kind of behavior in 3 dimensions. We could take a transparent box, figure 5, fill it with fluid, and disperse particles in it with the same specific gravity as the fluid so that they stay dispersed in the fluid and do not sink to the bottom. Then, by vibrating the walls of this box from all 6 sides in a synchronous manner, we could cause these particles to aggregate in a symmetrical 3-dimensional pattern. This pattern will look just like a highly enlarged crystal if we assume that the aggregated lumps are analogous to the atoms in the crystal. We have again produced a standing wave pattern in this box, which is a 3-dimensional analog of the standing wave in the string and the metal plate. At the same time, we have produced a 3-dimensional object analogous to a basic building block in nature and a highly ordered crystal. And we have done this simply by applying sound to an amorphous, disorganized suspension of particles. Hold on, let me get a sip of coffee. Fuck this all up. In the box, we have set up an inference pattern of standing waves, which we will soon explain, that governs the position of the particles. In short, by using sound, we have introduced order where previously there was none. It may occur to us that a crystalline structure may be seen as representing sound interacting in a volume. Is it possible that the orderly pattern of atoms in matter is the result of the interaction of some kind of sound waves in matter? I think that's enough for today. And don't worry, I'm doing this book probably a little more than usual. Same with White Goddess, because I just started it and I'm excited. Don't worry, I ain't going to forget the other ones. I don't leave a man behind. If I start a book, I'm going to finish it. Have a good day.